Okay, so today is day 6, and it's our first exposure, I guess you could say, to creating three-dimensional shapes. So today we're looking at volumes by cross section. So I have a card I'll put up on the board that kind of details this, but the idea of volumes by cross section is it's kind of bringing up an old concept. So I'm starting out the takeaway saying what's old is new again. The old thing is that if you add up thin rectangles, you get area, right? That area with that accumulation, so to speak, was the limit of those rectangles as they get skinnier and skinnier, and as we increase the number of rectangles to infinity. The new is if you add up thin prisms, you get volume. So we have models here. So the idea is, from the side, they look like thin rectangles, but because we, I'll get into the three-dimensional shape in a second, but what we really have in prisms, because we have three-dimensional shape. So how do we go about doing this? Well, what we do is we look at what I would call a foundation or a footprint, and that would be this. So if I tip it like this so that you can picture maybe the origin right down there where my finger is, that shape is what sort of shape? Parabola, right? So the idea then is that footprint or that foundation is lying flat on a horizontal surface. So I have flat on a horizontal surface my parabola, right? And on that parabola, I build up vertically. I build up the squares. So at some random location, that vertical section is this thin little prism. I'm just accumulating the prisms from bottom to top, or from some beginning point to some ending point, and creating that three-dimensional shape. So we're slicing it now. The way I have that drawn, I am perpendicular to the y-axis. So it's a dy problem, okay? Because that differential dx dy is the thickness of the rectangle in the old world, right? Well, that's just the height of the prism, so that prism in the middle. So that would be a dy problem. I could just rotate it 90 degrees and make it a dx problem. But then if I rotated it 90 degrees, I'd have some sort of square root function on the top and square root function on the bottom. That makes sense. So any questions about that? Okay, so today's focus then, I believe we're spending 2 days on this. Today's focus then is squares and rectangles. Okay, and so what we need to do is how can we adapt our knowledge of calculating area so that we can calculate volume? So what we're doing is we're taking the integrand and we're coming up with an area function. So when we talk about squares, the area of a square is side times side, or side squared. So this area function for a square then is quite literally the area function for a square is quite literally side squared, where that side relates somehow to the function that you're getting. It's either maybe we're going out from the axis to that function so that it's just the function value itself, or maybe we're, like in that case, we're straddling an axis going from a plus to a minus. So maybe that side is twice the function value. It's twice as long as the function value. So that area function gets related back to the function value. Okay, so we've got topic questions. We got notes to take. It's still going to be the same concept. It's just we're going to do different cross sections. I think it's triangles and semicircles or something like that. And so we can start making different, you know, if that was replaced by triangles, then we would not have this big boxy square thing. We'd have this thing with sloped sides. And so as you're going through the notes, you'll see me using a lot of 3D modeling and video clips that I made of those 3D functions modeled in GeoGebra to give you kind of an idea of what this looks like as a 3D model. Okay, so you can go ahead and get started on that. I'll come around and check in the notes and address any questions you might have.